Welcome to the Solar Eclipse video series covering the basics of solar photovoltaics or solar PV. My name is Drew Chavon. I'm an extension specialist with the University of Maryland, and in previous videos we assessed the energy requirements for various electrical loads that we might want to power, but in today's video we're going to learn how to assess the amount of sunlight that's available at any given location, and we're going to be using peak sun hours and a shade analysis in order to perform this assessment. Now, it's important to understand how much solar energy a particular location receives because we're converting the solar energy into electricity using a solar module. A solar module can produce a specific amount of power based on the actual sunlight levels, which constantly vary based on weather, seasons, and of course the cycles of day and night. So the only way to know how much electricity will be produced over the course of a whole year is to calculate the amount of sunlight power over time. So comparing the solar energy that's available on a site like this to the energy demand from our electrical appliances, it's really pretty easy considering that both forms of energy are measured in watt hours WH or kilowatt hours kWh.
Now we'll start by taking a look at this chart that shows a generic peak sun profile. On the bottom, the x-axis is the hours of the day, and on the up and down y-axis is the irradiance level in watts per square meter. While the actual solar intensity or power will fluctuate over the course of the day due to the sun's position in the sky, also due to clouds and other atmospheric conditions, the general trend will be the power level rises above zero at sunrise, it peaks at solar noon, and then it zeroes out once again at sunset. Now, we could find out how much energy is available over the course of a day by calculating the area below this smooth curve. We could try to do this using calculus, but for today's purposes, we'll explore a much simpler way to assess solar energy.
In this case, we'll use peak sun hours to express the amount of sunlight that our solar panel receives. The term peak sun hours refers to the number of hours in a given day during which the solar insolation is shining at a value of 1,000 watts per square meter. And we look at the number of hours that it takes to deliver that same amount of energy that we see under the actual smooth curve of solar intensity. So with peak sun hours, we're trying to determine how many hours in an average day the sun is shining at 1,000 watts per square meter, which, if you remember, this is the value that corresponds to the standard test conditions under which solar panels are rated.
While the actual plot of solar intensity over the day is a smooth curve, the concept of peak sun hours simplifies this math by compressing the solar curve into a rectangular block having a height of 1,000 watts per square meter. The width of this box then indicates how many hours the solar intensity is at 1,000 watts per square meter. This time frame, again, is known as peak sun hours. Now, obviously, this rectangular plot is not realistic because sunlight doesn't instantaneously peak at 1,000 watts per square meter in the morning, nor does it zero out instantaneously in the evening. It's not as if we can turn the sunlight on and off using a light switch. But in any case, this simulated rectangle produces the same amount of energy as the smooth curve since the area under both lines is equal. And you can easily evaluate the peak sun hours from an irradiation map. For example, we can see that Keedysville, Maryland receives 4.5 kilowatt hours per square meter per day. Since the peak solar radiation is 1,000 watts per square meter, the number of peak sun hours is numerically the same as this daily solar insolation. Hence, we can say that Keedysville, Maryland receives 4.5 hours per day of peak sun.
Now we'll take a look at where some of this solar irradiance data can be found.
We'll start by using the solar radiation data found in the Solar Radiation Data Manual on the National Renewable Energy Laboratory's website. A link has been provided in the description below. Obtaining the peak sun hours from this resource is rather convenient and accurate, particularly if you're close to one of the reported sites, but the accuracy will be somewhat impacted if you can't find a site that's near your actual location. For demonstration, I'll reference Baltimore, Maryland, located at about 39 degrees north by almost 77 degrees west. The bulk of the data that we're interested in has units given in kilowatt hours per square meter per day, which is equivalent to the peak sun hours. So these are the numbers that you would use to estimate the energy production of a solar electric system. Now, the data set that's used most often is for solar panels pointed due south, usually at a fixed tilt angle, which could be horizontal, that's 0 degrees, vertical, which is 90 degrees, or at latitude, latitude plus, or latitude minus 15 degrees. For our example, we'll consider a flat plate collector in the Baltimore area, and we'll assume the solar panel is facing south, with a tilt angle set at the latitude for Baltimore, which again is about 39 degrees. In this case, we would have an average of 4.6 hours of peak sun each day.
Now you could also use the NASA website that's linked in the description below.
On the left side of the page, we'll set the following configurations. To start, we'll select renewable energy as the user community and climatology as the temporal average. We'll then enter the latitude and longitude of our location, or we can simply mark the location on the map. Here I've marked our Research and Education Center in Keedysville, Maryland. In this case, no time window needs to be selected since we set climatology as our temporal average. For demonstration purposes, I'll simply select the ASCII format as our file output. Next, we'll select the parameters that we want to see. In this example, I'll pick the temperatures, so the meteorology option for maximum temperature at 2 meters and minimum temperature at 2 meters. And I'll also pick the solar irradiance at different tilts of the PV module. This option will allow us to see the degeneration for different tilt angles. Lastly, we have to submit all of these parameters. Now, an explanation of each parameter is shown at the top of the results, followed by a table of the actual results. In the first two lines, we have the maximum and minimum temperature given for each month of the year, as well as the annual averages. The next several rows show the solar irradiance for a tilt surface that is horizontal, or 0 degrees, latitude minus 15, latitude plus 15, and vertical, or 90 degrees. Then, in the final rows, we have the solar irradiance for angles that are optimized for each season. We have the angles that are needed to achieve that optimization. Now, these values are given in kilowatt hours per square meter per day. So, to determine peak sun hours, just divide these numbers by 1,000 watts, or 1 kilowatt per square meter, which in this case, again, would be the same number, just with different units. Now, you could use any number of other resources to get this same information, including NREL's PV Watts calculator or the EPA's Enviro Atlas.
Now, to receive the maximum solar energy, you don't want shading from any trees or other obstacles. So before you design or install a solar electric system, you should always conduct a shade analysis. Shading can come from any number of things, including trees, buildings, power lines, or other structures. If there's too much shade, then you'll likely need to remove that source of shade, or you could install your solar panels elsewhere. Now, it's easy to see the shading from the tree that's on my right, so this is probably not the best location to install a solar electric system. But how would you assess the shading from a tree like this at a different time of day or a different time of year? While we could spend a whole year taking notes on where the shadows are falling on this site, we're going to consider a more practical approach to assessing potential installation locations here at this site. Site assessments can be performed using various tools, including a magnetic compass and a sun path chart, but it may be more practical to use a professional site evaluation tool like this Solar Pathfinder, especially if you anticipate an assessment of multiple sites or locations. A Solar Pathfinder like this can quickly provide a full year of accurate solar data, with the shading analysis that you develop becoming a part of the permanent record of the solar data of that particular location.
We'll start by looking at a sun path diagram which shows solar installation data on an hourly and monthly basis throughout the year. Each diagram is latitude specific, with this particular diagram covering most of Maryland's latitude range. Now, the concentric arcs that go across the diagram show the sun's average path for each month of the year. The largest arc is for June, when the sun is at its highest. The smallest arc is for December, when the sun is at its lowest point in the sky. The vertical rays show the solar time going from about 5 a.m. to 7 p.m. The intersection of each arc and line represents a time during that month. For example, this point would be 10:30 a.m. in the month of September. The small numbers along each monthly arc indicate the percentage of solar radiation in half-hour increments. These numbers add up to 100% of the solar radiation that's potentially available during that particular month.
Now we'll use this sun path diagram in conjunction with the Solar Pathfinder to predict what % of the sunlight we can expect at this particular location through every month of the year. This device has to be positioned at the specific location as well as the height that we expect to install the system.
We'll start by rotating the unit until the magnetic compass is pointing north. Then we'll adjust for the proper magnetic declination of this location by rotating the diagram until it's facing true south. You may need to refer to a magnetic declination chart for your location. Links are included in the description. In this case, Keedysville, Maryland has a declination of around 10.5 degrees west of north. Then we'll level the Pathfinder using this bubble, and after replacing the reflective dome, we'll look from directly over top to see the entire skyline superimposed over the solar path diagram. We can either trace an outline of the objects that are reflected on the dome, or we could simply take a photograph from above. In any case, we can see when this location will be shaded or exposed to potential sunlight through the year. Shading occurs at any time that the reflection of an object intersects with the sun paths on the diagram. In this case, we have a shadow that's being cast on the location every morning from the building that's located on the east side, meaning that we won't have much sunlight at this location until sometime between 7 and 9:30 a.m., depending on the month of the year. And you'll have to ignore the hand gesture that's blocking the sun for this photograph, but this location does have another shadow from the tree that's on the west, and that's blocking most of the afternoon sunlight. If removing an obstacle like either of these is impractical, then you can simply move the Pathfinder to a new location that may provide better exposure. Now, looking at this new location, that same tree will block the sunlight after 1 p.m. in the winter months, while another tree is blocking the sunlight after about 2:30 p.m. in the summer months. So looking around the horizon, we'll see additional shade coming from the trees in the structure to the east. This shade is primarily an issue in the early morning hours. Now, we'll try one final location. In this case, we have a tree located directly to the south that's casting a shadow between 10 a.m. and 12:30 p.m. from about September to March. While this shading will certainly hinder your system production in the colder seasons of the year, the tree will at least have fewer leaves in the winter to allow more sunlight to come through. You can process any of this information that you gather using various software packages, or you can assess the data manually. To find the percentage of radiation for each month, we'll add the small numbers in the unshaded part of each sun path arc. Once again, these small numbers indicate the percentage of the radiation that's potentially available during the specified half hour. In this example, the tree to the south is blocking between 14 and 38% of the radiation depending on the time of year. Hence, this location may only be exposed to about 62% of the radiation that's potentially available. For a more thorough assessment, you may want to enter this information on a spreadsheet. In this case, I've entered the percent of radiation for each half hour for each month. The totals are calculated in the software, and we can see that we have access to less than 75% of the potential radiation in the winter months due to shading.
Now, picking the best option for your site will depend on what your specific goals are and what's more important to you. You may need to ask yourself if having solar power in the morning is more important than in the afternoon, or perhaps what time of the year you might want to use that power. Well, I'm Drew Chavone with the University of Maryland Extension, and I hope this video has provided you with an understanding of how to assess your local solar resource and any potential shading that you might have. This information can help you make an educated decision on where and how to position solar panels on your site, and it can be used to design, size, and estimate the performance of a solar electric system. You can subscribe to this channel to stay connected on upcoming episodes of this Solar Clips video series, but in the meantime, please visit our website for more information on solar, photovoltaics, and other energy-related topics.